Hello everyone, this is Dr. Kao. Welcome. Today we're going to learn a new topic called Logistic Regression. So here's the problem we have. We have the data about the user's number years experience, their annual salary, and we also know whether the account is paid or unpaid. So your job is going to build up a model to predict whether the account is paid or unpaid based on the experience and annual salary. We already learned several models like linear regression, right? So obviously you can come up with one solution, like beta account would be beta 0 plus beta 1 experience plus beta 2 salary plus epsilon. So you can do that. If you apply that multiple regression, what happens? So your prediction would be here, the x would be the predicted, y is the actual. So you can see the actual would be 0 or 1, either 0 or 1. But your predicted number could be less than 0 or could be larger than 1 because you have this multiple linear regression, right? So there is some issue of the model. So your output, we want to make it 0 or 1 to represent paid or not paid. However, the multiple regression cannot deal with that. So of course, you could figure out a way to make it happen. And also, linear regression assumes some errors were uncorrelated with columns of X, but it's not true in our case. Obviously, more experience leads to greater likelihood of premium account in our case. So this is a problem, and how to solve that? Today we're going to learn a new model. Okay, so the new model we have is called Logistic Regression model. So this is the model we have. It is a function called logistic function. So the function would be here 1 divided by 1 plus math.exp negative x. So that's 1 plus e to the negative x. So that is a function. The cool thing of the function, you can look at the picture here. The cool thing is this function will never be larger than 1 or less than 0. So it's always between 0 and 1. And another cool property for this function is we can always calculate the prime very easily. So for this logistic function, the prime would be the logistic function itself times 1 minus the logistic function result. So the prime is very easy to calculate. And why we need that? Because we already know the gradient descent, right? So if we can easily calculate the prime, then we can use the gradient descent easily. So this is the function we have. So the logistic model would use this function. So yi would be fxi beta plus epsilon I. So f is a logistic function we have. So our model said each yi should be 1 given the data with the probability of fxi beta, right? So it should be 0 with a probability of 1 minus fxi beta. So we can write the probability function pyi given xi beta. And of course, this probability function, sometimes in order to maximize the result, it's better to take a log. So we can take a log, and with the property of this log and the multiplication, we can get the formula. This formula have it here. So any beta maximize the log likelihood, also maximize the likelihood here. And we know like most of the time the gradient descent will do the minimization, but it is fine. We can just take the negative or multiply the log likelihood. So the negative log likelihood minimize that negative log likelihood would be the same as maximize the log likelihood, right? Okay, now let's take a look at some implementations.